Lucas, I'm going to ask a question. Yes, you can't hear it.
Yeah.
Okay.
All right. So it's a pleasure today to introduce to you Sekhar Chivukula. Sekhar got his PhD at Harvard in 1987. And then after that, he went to Boston University as faculty member. He was also faculty member at Michigan State. And then in 2018, he went to San Diego, where he's a distinguished professor of physics. Sekhar has worked on theories of electroweak symmetry breaking and applications of beyond the standard model physics, particularly in relation to LHC. And Sekhar is also an advocate for high energy physics, serving on high energy physics panels. He was DPF chair recently, and he also promotes opportunities for women and scientists from developing worlds. So he's really plays an active role in all these activities. So we're really happy to have him here today, and he's going to tell us about his recent research on symmetries of extra-dimensional theories and their consequences.
Thanks, Tony. It's a pleasure to be here. It's been a while since I've been in Minnesota giving a physics talk, and I'm looking forward to it. So by the end of this lecture, I hope you will understand what this diagram means. This represents if you have a massive spin-2 particle, which is a Kaluza-Klein graviton and some compactified five-dimensional theory. This represents the behavior of the scattering amplitude in terms of the incoming helicities and outgoing helicities of the particles. And the different color codes show the naive expectation, and then I'll explain what's naive about it and how it changes. But the naive expectation of how the scattering amplitude behaves at high energies as you go to energies, and in particular, the helicity zero. So this is if you have a massive spin-2 state, there's a state that's a helicity zero state. This helicity zero scattering amplitude, so spin zero, helicity zero goes to helicity zero. Naively, the scattering amplitude, as I will show you, grows like energy to the 10th power, which is not a very good thing for a quantum mechanical amplitude to do, since a quantum mechanical amplitude is bounded in absolute value by 1. And what I want to convince you is actually this theory has in it a fair number of subtle and interesting, I hope, cancellations amongst the different contributions to the scattering amplitude. And I want to convince you that those cancellations are a result of the underlying symmetries of the theory. This story may seem very familiar to you. This is very much like the story of what happens in the standard electroweak model, where the massive scattering of longitudinally polarized gauge bosons would also naively have a bad high energy scattering behavior. And that theory, because of the underlying gauge invariance, actually heals itself. And I'll review that and try to make the analogy with what happens in this case. So
Sekhar, I'm sorry to interrupt, but I think it's not a correct description of what's going on in electroweak theory. Because if it's a heavy mass, if it's hard mass there, then this longitudinal polarization would be indeed with growing cross section. So it's not only because you added Higgs mechanism to this, not because of what you said.
Thank you, Akedi. I take your point. You're saying, if I understand what you're saying, what you're saying is that it's that the theory really only has an underlying gauge symmetry in the context of
gauge symmetry is not enough.
Yeah, gauge symmetry is not.
Because massive vector gauge field would be still non-linearizable, right?
Correct. Mm-hmm. Yeah, but I mean, a naive mass would, of course, break the gauge symmetry as well. But you mean with a nonlinear sigma model, you can interpret the mass as having a nonlinear sigma model, and then it's the underlying behavior of that nonlinear sigma model that you're seeing.
Right, but the price is that they introduce extra particle, right?
Extra particles, correct. Yep. So no, these are good questions. Maybe I can come through and we'll come to an agreement, or not. We can discuss more as we go along. Is that okay?
I'm sorry to interrupt.
No, wonderful. Good to hear your voice. I'm glad to hear. I hope things are going well in Santa Barbara. Okay, so let me tell you the motivation. We started on this project almost 5 years ago, and we thought we had a very simple cleaning up or investigation of a standard scenario that we wanted to understand better, and that had to do with understanding the properties of dark matter, which was connected to the standard model only through the gravitational sector, and in particular through some kind of a gravitational Kaluza-Klein exchange. And we were going to do this in the context of the Randall-Sundrum model. In the Randall-Sundrum model, one has it's a five-dimensional theory, at least naively, where the fifth dimension is a compact extra dimension with a non-trivial warp factor for that extra dimension. And this non-trivial warp factor, of course, phenomenologically, the reason you're interested in it is it provides a gravitational redshift in this across this extra dimension, meaning that if you a scale of order, say the Planck scale at one end of the theory could correspond, if you have enough warping, to the electroweak scale at the other end of the theory, and therefore, if your electroweak particles, if your Higgs particle, for example, is a composite state or some kind of a state localized on this end of the interval, it would be natural that its scale would be of order a TeV, and it maybe doesn't solve the hierarchy problem, but at least readdresses this hierarchy problem in terms of constructing this gravitational redshift. So that was the context in which we were going to look at this Kaluza-Klein dark matter. Anytime you have an extra dimensional theory that's compactified, then all of the fields that live in the extra five-dimensional theory get resolved in the compactified effective four-dimensional theory into a tower, a Kaluza-Klein tower of states for these extra dimensional theories. So, for example, the five-dimensional graviton contains within it, after you decompose the field, the five-dimensional field, into a series of four-dimensional states, it becomes a tower of four-dimensional massive spin-2 states. You would identify the lightest such state with the graviton, and you have ordinary, and that generates ordinary general relativity. And then you might potentially have you would look potentially for resonances of these Kaluza-Klein gravitons at the Large Hadron Collider. It depends on the details of exactly how the standard model interacts with and is embedded in the extra dimension. But you could, in principle, have states, say, where gluons fuse to form these massive spin-2 states that then decay. And to the extent that we know we do not see these extra resonances, we have constraints on the kinds of extra dimensional theories that we have. So this is kind of naively the setup we had in mind. The idea would be that you have, the low energy brane, and maybe dark matter sits on this low energy brane, the standard model. Some pieces of it could be in the TeV brane, some in the bulk, or some in the high energy, at the high energy brane, depending on various phenomenological constraints that you want to impose. And the idea would be that the dark sector only talks to the standard model through gravity, through the Kaluza-Klein, and in principle also the massless graviton, but the interactions of the massless graviton are typically not relevant since they're suppressed by the Planck scale. Because of the warping in the extra dimension, the interesting part of the properties of these extra dimensional Kaluza-Klein gravitons is their interaction scale is actually set by the TeV scale. Their wave functions, when you look at it in extra dimension, are localized toward the TeV brane, and effectively the scale of interaction that suppresses it, and it was sort of here implicitly, the scale of interaction that suppresses the interaction of these KK gravitons, these Kaluza-Klein gravitons, either in principle with the standard model or dark matter, this one depends exactly on how the standard model is embedded, but the characteristic scale would be of order the TeV scale. And that means they could have potentially interesting signatures. We know that the WIMP miracle is getting more and more constrained, but we know that if you end up with a cross-section in the early universe for the interaction of your dark matter particles, in particular the annihilation cross-section of your dark matter particles into standard model particles in the early universe, with this kind of an overall cross-section, then you can have a relic abundance of these dark matter particles that saturates the relic density that we see of dark matter. So this is a long way removed from what I'm actually going to talk about. I'm basically going to be talking about what's going on in this sector, but this was our motivation, and the reason, the connection between the motivation and the calculation was that, so first of all, I should say we were not by far the first people to think about this kind of scenario here. a set of 5 papers, including one by Keith, on this kind of a scenario. And what confused us was that when you look in detail at the kind of interactions that you need to understand in order to understand the behavior of the dark matter particles in the early universe, one of the things that they can do is annihilate potentially back into Kaluza-Klein gravitons. And we thought, oh, this would be a fairly simple calculation. We should just do it and check and make sure that we understand what's going on. And when we did that, we found that this amplitude behaved in a way that was far from what we expected. In fact, when we just did it naively, we found that the amplitude grows like energy to the 6th power, and I'll explain where all of this scaling comes from in a minute. And that actually kind of invalidates sort of the kind of analysis that had been done in the past. And so if these processes actually are important and do grow like energy to the 6th, the behavior of these particles in the early universe is very different than we would have expected.
So the other thing is, they miscalculate, or they just didn't pay attention to it, or they missed it?
It depends on the paper that you're talking about. So in Keith's paper, I'll talk in a minute, they didn't consider these. And in fact, it turns out to be right. There's a reason that these end up not being relevant, but we were trying to check that. And in some of the other papers, they assume that it really goes like energy to the 6th and try to estimate what the effects of that would be. So it depends on exactly which paper you're talking about, but you get different behavior.
But it was triggered by this.
Nobody was triggered or as obsessive as we were to try to figure out what was really going on. And that's
May I ask you, at this point, because the main difference between this expected behavior and the one you are writing, E square or M Planck square, is that this amplitude, the second one, has a limit at m equals 0, right?
correct.
The first one is, is singular at m equals 0, right? Is it a generic feature of this, or it's just for this particular example?
It's a generic feature, diagram by diagram, that the amplitudes appear to have that behavior. But what I will convince you, I hope by the end, is that the theory is smarter than that and doesn't actually end up behaving that way.
Yeah, but it means that the theory allowed massless limit right away, right? In certain.
Eventually, once you do the calculation correctly, yes, the massless limit does exist.
I see. Okay. No, it's what was. Thank you.
Yeah, sure. So if you think about it more carefully, so this is just saying, I think what I said for Maxime, that if you only consider these diagrams, then the coupling between the gravitational modes in the standard model is through the energy momentum tensor, which is conserved. And because the energy momentum tensor is conserved, that takes care of the bad high energy behavior. The problem actually comes from these self interactions of the gravitons amongst themselves, because naively, just like in QCD, naively the QCD current where the gluon couples to itself, naively it doesn't satisfy the naive conservation law that you would need. So you need to actually make sure that you take into account all the degrees of freedom and the symmetries of the theory consistently in order to get a consistent scattering amplitude. And so I just want to remind you, and then Katie, you can say whether I'm saying this correctly. I want to remind you that a similar sort of behavior occurs in the standard model. Tony said that I had done work on electroweak symmetry breaking. It's true, I did, but I usually have to admit that I spent most of my career trying to convince people that there wasn't a Higgs boson. I was overtaken by events and so what's that? I recalibrate, yes. So this is motivation that before the Higgs boson was discovered, all of if you're in Tony's class on the standard model, he probably would have covered this at that point, and we would all have said that this was that we were trying to convince the United States government to build the superconducting supercollider, and our reason for that was we said, look, the standard model with just massive W and Z bosons themselves isn't consistent to arbitrarily high energies, and you can do that by just looking at the scattering amplitudes of W bosons with themselves, right? Since it's a non-abelian gauge theory, the W bosons interact with themselves. That's what makes them different than the photon. So there's, in fact, naively, if you just write down, there's a contact interaction, you can exchange a Z boson or a photon. And this L here is to remind you that what I'm interested in is the longitudinal helicity polarization of the W boson. And now that's important because the longitudinal helicity polarization at high energies has the property that the longitudinal polarization is essentially proportional to the momentum of the particle that's coming in. Now, if this object is then coupling to a conserved current, then this behavior is not important to you because the K mu acting on that is just the divergence of the current and gives you 0. However, in these diagrams, naively, this term does not cancel because, in fact, the naive, if you write it, I guess the correct way to say it is the non-abelian SU2 current is not abelianly conserved. The covariant derivative is 0, not the partial derivative, right? So naively, this would cancel against something at some higher order or a different kind of a process. Now,
No. If you see, it goes one by one. In particular, recollecting my own history with Hiplovich in 1970, we started. I don't know. I'm trying to remind you that Tini Weltman was the one who said that the theory of massive vector field is renormalizable. He got this citation of Nobel Prize with quote for him refers to this paper, which was wrong, because he said that this hard mass vector particle is a renormalizable theory. And the point was that if you consider what we wrote, K mu over MLU, at level of one quanta, it certainly would be like a billion, right? It would go away because of conserved current. When you have two of them, I mean, say two vector boson, right? Then you have two different K divided by M, and the leading term for when this K mu cancel out, and then you have another one, but you also have term proportional to MW, which you wrote, right? The next one. So then the amplitude with 2W boson would be 0 order in MW, because you have 1 over MW from the second, and you have a proportional to MW from one of those, right? So the general behavior is that the amplitude behaves as energy in the power number of W boson minus 2.
Yep. Exactly. That would be the next slide.
Yeah, right. But in this sense, how to say, but in this sense, how to say, conservation of current does work in the sense that it gives you a number of W boson minus 2. So in terms of loops, it corresponds that in vector theory, start from the second loop. The first loop is still kind of renormalizable, right? And it is what Weltman said.
Exactly. So I'm only doing the tree level version of this, where you're seeing the same thing in terms of the behavior of the high end.
But we also did it in terms of tree level, right? You're right. But you can conclude for arbitrary number of W boson.
Yep. So to summarize, at least my view of what I think Arkady is saying is just when you look, if you look at this diagram naively, if you just think about calculating this diagram, you have 4 powers of this external momentum. So this diagram alone, if you simply calculate it in unitary gauge at high energies, has a piece of the amplitude that grows as fast as energy to the 4th. Now, in the non-abelian vertex here has no derivatives. It's just the product of F symbols. Whereas these diagrams also grow like energy to the 4th. Where does the energy to the 4th come from? There's 1 power of energy from each of these vertices. And then in unitary gauge, this propagator goes like, just goes like a constant at high energies. So in the end, these all go, and then there's 1 over energy. So in the end, these all go like energy to the 4th. And when you look at the leading term, the energy to the 4th part of the term does in fact cancel. And that is a reflection actually of the Yang-Mills structure, because the coefficient of energy to the 4th essentially is proportional to the Jacobi identity of the gauge theory. So it is a consequence, and I think this is exactly what Arkady is saying, which you would naively have thought like should go like energy to the 4th, which is the leading divergence you would expect. That vanishes directly because of the symmetry. However, that's not good enough, because the amplitudes in quantum mechanics should stay bounded. So you also, if you expand to subleading order, there's a term that goes like energy squared. And that term like energy squared is in fact non-zero. The term coming from energy squared from these three give you these contributions proportional to the energy squared here. And they don't cancel. And that means something else has to come into the theory at some level in order to actually unitarize this amplitude and to leave it consistent with quantum mechanics. And this is one way you can motivate the existence of the Higgs boson. The Higgs boson comes in with couplings precisely tuned so that this amplitude cancels, the order energy squared cancels. From this point of view, it's kind of a miraculous thing that you can do it at all, but it's really built into the renormalizability of the theory to start with. So it will come out automatically from the renormalizability of the Higgs theory. Now, from the old point of view, before the Higgs boson was discovered, this gave us some sense of the energy scale by which something has to come in. And the argument was something must come in by of order a TeV, and you can argue whether it's a TeV or 500 GeV or 1.5 TeV. But that was the motivation for the energy scale of the SSC and the Large Hadron Collider ultimately was to do that. So this little prehistory is just to tell you that there's a relationship between how the masses occur in these non-abelian interacting gauge theories and the behavior of the scattering amplitudes. And so actually almost 20 years ago, a little more than 20 years ago, Hong-Jun He and I and Dwayne Dicus and a few people thought about another possibility, right? Sort of how is this related to the fact that you can have massive spin-1 interacting particles if you take a Yang-Mills theory and you compactify that in 5 dimensions. Compactified Yang-Mills theory in 5 dimensions also has massive gauge bosons in it. And what happens to the scattering amplitudes in these compactified Yang-Mills theories? And this is a very simple compactified theory. Basically, this is just a Yang-Mills theory compactified on a cylinder. In fact, more than a cylinder, we're going to do an orbifold projection to identify opposite sides of the cylinder. And then the KK expansion in this case for the 5-dimensional gauge theory is just a Fourier expansion in the extra dimension. And each of the coefficients of the Fourier expansion are the Kaluza-Klein effective 4-dimensional fields in the theory. And you can kind of see what's going on here. There is a Higgs mechanism going on here, a 4-dimensional Higgs mechanism going on here. And if you expand, if you plug this expansion into the kinetic Lagrangian for the 5-dimensional Yang-Mills theory and integrate over the 5th dimension, what you find is exactly this kind of a term where, in a sense, you can see that the longitudinal part of the nth KK mode, the nth Kaluza-Klein Yang-Mills mode, is actually just the derivative of the A5 field. And so there's you can go to a unitary gauge where you set A5 exactly equal to 0, and then A5 vanishes, and all you have is a tower of massive spin-1 modes. And I'm going to come back to this in a minute. This allows you can actually write down an equivalence theorem, and you can understand the properties of the scattering amplitudes of these massive spin-1 states in terms of the amplitudes that would have been there in terms of the Eaton A5 Goldstone bosons.
But A5 is not the one which would play the role of Higgs, or what?
Well,
Hold that question for just a minute, Arkady, and I'll answer it.
what I was going to say, this is a U1 theory, and what
This could be any theory. This expansion is true for a non-abelian theory and an abelian theory. It's fine. We're going to use it for a non-abelian one.
okay, but then this is more like it's not really Higgs because there's no Higgs boson.
Hold that. That's related, I think, to Arkady's question too.
Yeah.
Okay. So a theme of this is when you don't know what to do, just calculate and find a student who's actually capable of doing the calculation. This calculation even I can do. This calculation is what happens if you consider the longitudinal scattering of, say, Yang-Mills gauge bosons at level n. Okay. Remember, so here, this A is just the index over the adjoint of the gauge field. And then you have a tower of massive modes. And in fact, the masses are just multiples of 1 over r in this case because it's a flat extra dimension. And the kinds of interactions you have a contact interaction just like you had in the standard model. you have gauge interactions. In this particular case, because it's a flat extra dimension, there's actually a discrete momentum invariance in the extra dimension. Or another way of saying it is just, integrals of even numbers of cosines. You need an integral of an even number of sines in order to have a non-vanishing overlap integral. But anyway, so when you do this, you find that at level n, the only coupling, the only 3-point coupling at level n is for 2 level n to go to either level 2n or level 0. Because those are the only things that satisfy discrete momentum conservation. And so you have these 3 diagrams. And when you add these diagrams up, you find the energy of the fourth cancels for the reason Akadi already discussed. There is an unbroken gauge symmetry. But you also find the order energy squared cancels. And the order energy squared cancels because of this additional contribution here. And then when you add all of these, you find that all of the energy squared terms cancel, and the leading contribution in this compactified Yang-Mills theory goes like a constant at high energies.
I see. So this A mu 0 plays a role of Higgs, right? Or effectively.
The A2N0 is playing the role of the Higgs, but I also agree with Tony, it's not exactly a Higgs. And one way you can see it's not a Higgs is where the interesting question is, could this ever terminate, right? Because in the standard model, you have the W and the Z, and you might say, well, if I scatter a W and Z, I must have an extra particle. But if you look here, level n and level n require level 2n, but that means level 2n with level n requires level 3n. You can never stop, right? You must have an infinite tower. In fact, this was also known, right? There's even I think in the literature, I forget who it was. I think it was Weinberg. It's the sort of thing that I would think Stephen would have done. He showed that the only way that you can get the terminates is to have a Higgs. But if you allow the possibility of an infinite number of sort of interleaved states, there's cancellation across the different KK levels that allows this amplitude to go like a constant at high energies. Now, you can ask, is this fundamentally a renormalizable theory or not? No, it isn't. It's still fundamentally a 5-dimensional gauge theory, right? A 5-dimensional gauge theory is not renormalizable, but this allows you to potentially build a Higgsless model. This is one way of viewing what a Higgsless model is. It allows you to build a Higgsless model where you adjust, and this was work done by Chaba and John Turning and Hitoshi and Hilo, yeah. Where, we just looked at a very simple case, right? Where we had this kind of a flat extra dimension. We took very simple boundary conditions that we imposed on our overfold, but you can actually find that it applies to any manifold with 5D invariance. You can vary the boundary conditions. You can get different, you can calculate the overlap, and it's still true that the scattering amplitudes only go like a constant at high energies. And by adjusting the boundary conditions, you can make the W and Z much lighter than the next state that you need. And that was the idea in a Higgsless model, is that maybe all you saw was the W and Z and the photon at low energies, and the next state was the state that would that the SSC or LHC would uncover.
Sekhar, may I ask you at this point? It's about symmetry, because the way, for example, when we did it with Hippolyte in 1970, was resulted that if you have massive, say, vector field, right, spin 1, then longitudinal polarization of this field, consider this then you will see that effective Lagrangian for just zero helicity field, it is nothing but SU2 cross SU2, no, in SU2 theory, it is SU2 cross SU2 chiral Lagrangian, the same as for pi. Okay, so the symmetry of helicity 0 is not SU2. No, I mean, okay, it's how to say, it's like chiral symmetry to SU2 cross SU2. Okay, so in this way, this longitudinal polarization are similar to pion. No, I mean triplet of pion in this case, right? Okay, but
this is kind of anticipating your question here.
No, but let me finish the point that it is so the symmetry is this SU2 cross SU2. Okay, now we know representation of SU2 close to SU2, we can discuss it, and PIM, it is non-linear realization of SU2 close to SU2 symmetry. And we know that we can go from chiral Lagrangian, we can go to linear sigma model if we add representation of SU2 close to SU2, which contains, besides PIM, contains sigma, I mean, additional field. It is the same symmetry. However, now there is chiral Lagrangian was automatically non-linearizable, but when we add the extra field, then we can make it linear. And it is still applied to your example in this sense, if you consider spin one, right?
There's an analogy, but the difference is that from the four-dimensional sense, this is really SU2 at every point in space-time in the fifth dimension, right? It's not just one SU2 or number; it's an uncountable number of SU2s with respect to the four-dimensional picture. And
no, but for the low line states, let's consider, say, this the lowest in this KKK chain. Then I agree that it would be kind of more particle, whatever. But if I choose limit myself by the lowest ones, then it should be one-to-one correspondence that with so you have three helicity. You have a triplet of helicity states, and you are looking whether there is in this way additional scalar field which would be playing a role of sigma. So something like that should be there in your construction.
And there is I guess in that language, what I would say is the analog of the sigma is the longitudinal part of the A2N, the first resonance that the W and Z are exchanging. That longitudinal, that helicity zero part is playing the role of the Higgs in this case.
I see. Okay. You answered my question. Thank you.
Oh yeah, sure. Again, to emphasize though, in this theory, right, that longitudinal thing comes along with other helicity partners whose interactions would force you to again go up to a higher level in KK mode, and you can't. Unlike in the standard model where you stop with the single Higgs sigma-like or scalar particle, here you wouldn't.
Yeah, I understand.
It's not like there's a scalar with them. It's not even, that's the difference.
There's that, yes, exactly. So we know from in our work in the standard model that we can also think about the scattering of high energy longitudinal W and Z bosons in terms of the equivalence theorem. We know that at high energies, those scattering amplitudes are equal to the scattering amplitudes in the Topf-Feynman gauge for the unphysical Goldstone bosons that are in Topf-Feynman gauge. And that actually makes the scattering diagrams, that makes power counting easier to understand. If I do the analog here, the Goldstone bosons are the longitudinal parts of these scalar A5 particles, and their interactions with the vector boson have just one derivative in them. And the Topf-Feynman gauge, the propagator of any massive state just goes like 1/e². And so again, the scattering amplitudes are more transparent in a Topf-Feynman gauge, and using the equivalence theorem, they go to a constant at high energy. So everything is consistent. There's a consistency between the properties of the unitary gauge and the Topf-Feynman gauge calculation. So it depends on the underlying gauge invariance of the theory. No, I really mean the sum of all of them. It's the sum of all of them here is equal to the sum of all of them here. Yeah.
So why don't I have the contact either?
Because there is no 4A5 contact term because of the anti-symmetry of the way that it comes into the interaction. Yep. Okay, so this is great. I won't get through much of my talk, but let me get to the I want to now use the same reasoning, right? The reasoning was we were interested in the high energy properties of massive spin 1 and spin 2 particles at high energies. And the massive spin 1 particles, we saw that we could get cancellation among different Kaluza-Klein modes when the massive spin 1 particles were the Kaluza-Klein particles of a Yang-Mills gauge theory. And so now the question is, what happens in a spin 2 theory for scattering of Kaluza-Klein gravitons. So let me just remind you, and this is, I know Arkady has a lot to say about this, so I hope you will chime in when needed. If you just think about the number of degrees of freedom, a massless spin 2 particle in 4 dimensions has 2 degrees of freedom. If you have a massless particle, a spin 2 particle in 5 dimensions, it has 5 degrees of freedom. Furthermore, if you have a massive spin 2 particle in 4 dimensions, it would have 2L plus 1 or 5 degrees of freedom. So there's an interesting, and it always happens, right? There's an interesting matching between the number of degrees of freedom of the massless state in one extra dimension with the massive state in one dimension below it. And now you can ask just what happens if you try to add a mass term in general relativity. The simplest mass term you can write down, so this field h mu represents the spin 2 fluctuations above the background metric, which you take, say, to be just flat. And then the simplest mass term you can write down was initially written down by Fierz and Pauli, that Fierz and that Pauli, many years ago. And if you there's only essentially one combination that you can write down that's ghost-free in flat space, and it's this combination that you need to write down to avoid the possibility of a ghost. And now, if you ask yourself, if you just close your eyes and calculate, and you ask yourself, what happens when you take a Fierz-Pauli massive spin 2 particle, and you imagine that all of the interactions of that particle come from the Einstein-Hilbert action. So you take the Einstein-Hilbert action, and by hand, you add a mass term for the fluctuation. You don't expect this to be a well-defined theory, but you'd like to understand what the properties of this theory are. If you do that, and you simply write down the diagrams, it turns out that diagram by diagram, actually diagram by diagram, they go as high, they go like energy to the 14th to start with, but there is a cancellation because of the underlying, just like, remember the energy to the fourth, as Arkady pointed out, the energy to the fourth canceled in Yang-Mills theory to energy squared. That energy to the 14th becomes energy to the 10th, when you actually write down and add these things down. Now, you can say correctly that this was kind of a strange thing to do. I added this non-derivative term. I could add polynomial terms as well, right, beyond this, 3-point terms and 4-point terms. And you could ask yourself, could I write down 3- and 4-point terms that can change that behavior? Turns out the answer is yes. You can write down 3-point and 4-point interaction terms that don't involve derivatives. So these are, if you want, potential terms for this term H. And you can get it down as far as energy to the 6th that way, but you cannot go any further than energy to the 6th in this kind of a Fierz-Pauli theory. And this, again, remember, this is a very naive tree-level analysis. We have no idea whether this theory makes sense non-perturbatively or anything. This is just trying to understand the properties of the scattering amplitudes.
Yeah, no, but you can, what you're saying is analog of what was in spin 1, right? Because you can say that you still have conservation of current, energy momentum tensor, and it allows you to diminish this power, right?
Right.
So it's very much similar, right?
Exactly. And so we want to exploit this analogy, and we want to understand what happens to this analogy when we actually look at the full Kaluza-Klein state.
Mm-hmm.
The similar kind of thing, if we go back to what actually motivated us, if you have matter scattering, if you just do the calculation, you'll find that it goes like energy to the 6th. So that's what I was saying before, is what happens. So now what happens in a full Kaluza-Klein theory where you think about the scattering of massive spin 2 particles? So you now have to do a Kaluza-Klein decomposition for the fluctuation of the graviton. The 5-dimensional graviton in this around some background geometry. The background geometry we're going to take is RS. Whenever you do this kind of a calculation, in fact, this happens in cosmology when you worry about density perturbations in the early universe, you have to be careful to make sure you parameterize your theory in such a way that you properly diagonalize and get rid of the mixing between scalar terms and tensor terms. We're going to take we're going to do this on an orbifold background, just like we did, just to simplify the analysis. When we do that, we can impose an orbifold condition, which allows us to set these. So this upper block is a 4x4 block. This is a 1x1 block. This is a 5x5 metric tensor. Don't worry so much about the parameterization, but basically H mu carries the spin 2 fluctuations of the around the background metric. This U carries the scalar fluctuations, and because of the orbifold conditions, the vector contributions, which would be here, which would be in the fifth column, the first 4 rows, or the fifth row, the first 4 columns, can be set to 0. And if you want, you can think of that as a unitary gauge-like condition on this kind of a theory. So the only physical fluctuations are going to be fluctuations of the metric, and then fluctuations, scalar fluctuations that are left over. And in fact, there's going to be a little more that we can get rid of ultimately. So then you write down all of you plug this expansion into the Einstein-Hilbert 5-dimensional Lagrangian. You compute what are all the quadratic terms. You figure out what kind of a KK mode expansion will diagonalize the quadratic terms that allow you to actually figure out what are your Kaluza-Klein modes. And you still have some residual gauge degrees of freedom that you can fix in the background. And what that eventually tells you is that the actual degrees of freedom of this theory are a tower of Kaluza-Klein modes, starting with a graviton of mass 0, and then a tower of massive states. And you have only one 4-dimensional state. All of the Kaluza-Klein excitations beyond 0 mass in the scalar sector can be essentially through a gauge fixing, they end up being modes in the spin 2 field. So there's only one object, the radion. This is typically called. There's one 4-dimensional massless spin 0 field, which is typically called the radion. And then there's a massless spin 2 field, and then there's a tower of massive spin 2 fields. That's the physical content of this theory. The masslessness of this radion can be understood by the fact that in this naive sort of Randall-Sundrum background, there's nothing that sets the distance between the two ends, the physical distance, the proper distance, if you want, between the two branes of the extra dimension. And so fluctuations in that direction are unconstrained. And this scalar degree of freedom corresponds to fluctuations in that direction.
This is what you call H55 in the flat field.
Yeah. The tower turns out to be through gauge fixing, you can set the tower to 0. There's just the massless mode that's left. Yeah.
If you have some stabilization mechanism, like
yeah, I'll show you that later. But yeah, that turns out to be a far more complicated problem. But okay.
But on in different language, you see, when you would consider just 4-dimensional theory, not going from 5th dimension, there is this kind of what's called Zakharov, Weltman, Van Dam discontinuity, that the limit when you have Pauli fields mass, which you discussed, then taking the limit when m goes to 0, you are not coming to m equals 0 amplitude, right?
Right.
Okay. Here in your case, you have still masses graviton, and in this way, I wonder whether you have a parameter that's similar to this mass which we are discussing, kind of limit. You still have this parameter of the mass, or it's something else in this approach.
The parameter, the real parameter is in some sense this size of the extra dimension.
Yeah.
To set the mass scale, but you're certainly right. This does not give a realistic theory of 4-dimensional gravity because it's Brans-Dicke gravity, right? It's got a massless scalar as well as a massless spin 2 field. So this is not a phenomenologically acceptable theory of
yeah, but it is still would be massless gravity theory, right? Even Brans-Dicke, right? Or not massive one. I mean, for the lowest excitation.
For the lowest excitation is purely massless, yes. Massless spin 2 and massless spin 0.
I see. I got it.
Yeah. So these are the sets of interactions. So again, there's no imagination in this. The motto is find a graduate student who's good enough and willing to actually do the calculation and see what happens. It took us a while. But this is the kind of interaction that you get from in the 5-dimensional term. in the 5-dimensional sense, you can have couplings between the scalars and spin 2 fields, or 3 spin 2 fields, or 4 spin 2. Actually, this is just the beginning of an infinite tower because you're actually expanding the Einstein-Hilbert action out in the weak field approximation. But for 2-to-2 scattering, these are the only kinds of interactions that are going to be relevant to us. When you decompose these into Kaluza-Klein modes, you have a coupling of the radion to any 2 spin 2 modes. And again, one of them might be 0. It could be the graviton, or it could be any massive spin 2 field. You can have couplings between 3 massless spin 2 fields. I'm sorry, three spin 2 fields, or 4 spin 2 fields. And because of the fact that this is in Randall-Sundrum, you no longer have any kind of a discrete momentum conservation. One way of thinking of it is all of these wave functions are Bessel functions, and all of these Bessel function overlaps are non-zero. There's no simple reason why any of them vanish. They have lots of interesting properties. If roughly speaking, if M and N are low and K is high, eventually they'll go to 0 because all Sturm-Liouville solutions oscillate at large order. And so the overlaps do go to 0 ultimately, but they're not strictly 0 in the way they are in the trigonometric case.
With some over.
So what I will argue by the end to convince you is that the properties don't actually depend on the simple RS form. But for us to do the calculation to start with, we started with the simple form because we could figure out all the overlaps. But we didn't even know what the properties were going to be to start with, so we were restricting that. But in the end, as long as it has this sort of warped form, everything will come out. Okay, so these are the diagrams that you have to compute. And I'm just going to show you some results for the scattering of the first massive spin 2 mode, elastic scattering of the first massive spin 2 mode. So this is KK mode 1, KK mode 1, scattering to KK mode 1, KK mode 1. It can either exchange a radion. Remember, this is a single 4-dimensional field in this, in basically in unitary gauge, basically, of this theory. It can scatter by the exchange of any other spin 2 mode, including the graviton. So actually, this is going to have some T and S channel, I'm sorry, T and U channel singularities in it. It's not that relevant to us, but if we're there. And then there's, the 4-point interaction just coming directly from the expansion. And no, there is no conservation of KK number. So in the plots that I'm going to show you some results of what the scattering amplitudes look like. Show you sums depending on higher and higher numbers of these exchanged KK modes, because ultimately the theory, the full behavior is the sum over all of these modes, right? The full tree level amplitude, and we can't do that. We just have to do some numerical truncation.
Sorry, you might have said this, I just forgot. You still have a massless graviton.
You, yep.
So you're just taking the second lightest.
Correct. But we're including the massless graviton in the intermediate as an intermediate state. Right, because we're interested in understanding what the properties of a massive spin 2 scattering looks like. Yeah, and this was just the simplest state. So
you mentioned the T and U channel singularities in the second class. And that concerning you, but can you briefly comment on you're starting to have the behaviors of the amplitude?
Yeah, we'll look at some nominal scattering angle so that we're away from the singularity. Yeah. That's all. Okay. So what we're going to do is we're going to take our scattering amplitude, which we compute numerically, and we're going to look at the properties of the scattering amplitude order by order in moment in energy, center of mass energy squared. So we expand our scattering amplitudes, the full scattering amplitude summed over it. And remember, I showed you that naively, the diagram by diagram, there are contributions that go like S to the 5th. So the leading contribution is this M5 contribution. And here's the answer to Jen's question. We look at it over a whole cosine theta, so we can see where the singularities are and things. And this is summing over, this is only one intermediate KK state. This is over 40, this is over 100. You're seeing we're summing over more and more KK states. And this is what we found. We found that you have a non-zero amplitude. The overall amplitude is arbitrary, but you notice that by the time you sum out to 100 kk modes, you've decreased by 20 orders of magnitude. For a physicist, that's zero. As long as you're convinced that you're not in your numerical noise, right? It's basically zero. Okay. So after having summed over all of the kk states, you find that the contribution that goes like energy to the 10th power, S, center of mass, energy squared to the 5th power, vanishes.
But then you should have analytical statement of this kind, right? For the total sum.
I promise it's coming. Okay. I'm trying to build up suspense. Okay. The next order is S to the 4th or energy to the 8th, saying that you start to see some peaking behavior, right? These are, some T or U channel things going on shell. But you again see that the energy to the 8th cancels. Okay, in for a dime, in for a dollar. Let's go for energy to the 6th. Energy to the 6th cancels. Energy to the 4th. Energy to the 4th cancels. As Arkady says, there's got to be a reason for this to happen, right? This doesn't happen by accident, and this is what we'd like to understand. Uh-huh.
Do they vanish when you have more?
Yeah. Yeah, what I'll show you is that actually, I mean, there is an exchange of limits problem. I suppose if you started on the T-channel singularity, you're adding an infinite number of infinite things, and I'm not sure what you mean. If you go slightly off of that, what I'll show you is we have an analytic expression for the coefficient, and we can show the coefficient vanishes. Yeah. The same kind of, this skipping forward several years, you can do the same kind of thing in the dark matter calculation, in the matter calculation, and you can show that the energy to the 6th and the energy to the 4th cancel here as well. And the residual amplitude only goes like energy squared. So as Arkady anticipated, right, ultimately the high energy behavior of this theory is determined by the fundamental Planck scale of the theory, and it goes like energy squared. It's not some inverse power of mass that would seem singular if you're trying to make take your mass to zero.
So if I just naively do calculations, the 5V with which is much above the.
It'll just go like energy squared.
Yeah. I get what you expect.
Exactly. I mean, this is part of at least my intuition was that high enough energy should be probing essentially flat 5-dimensional. It should go like a constant. So that was why. How do I reconcile the fact that term by term in my amplitudes things seem to be going very badly, but at sufficiently high energies, it should again go like a most energy squared. That was. So now to the question, what do we know analytically? Here's what we know analytically, and I need to step back for a minute. If you look in Tony's Tazi lectures, or you look at it in lectures about how you deal with Kaluza-Klein theories, you find that the mode equations that determine the masses and the wave functions of the Kaluza-Klein modes are Stern-Liouville problems in your extra dimension, in terms of your extra dimensional coordinate y. And this is the Stern-Liouville problem for the RS model. That's why this thing is just the warp factor. This is the warp factor squared. So if you had any e to the a minus ay, anything that had that sort of it's non-factorizable, but it has RS-like form, you have an analogous Stern-Liouville problem. And everything is going to just depend on the properties of that Stern-Liouville problem. So that's the sense in which it's independent of the gravity in the extra dimension. Now, I've written down the modes, the equation corresponding to the spin 2 modes, and we're choosing, of course, to keep we want to have 4-dimensional gravity. If we want to have 4-dimensional gravity, the appropriate boundary conditions on the spin 2 fields are Neumann and extra dimension. So a flat mode will have 0 mass and will correspond to your graviton in this coordinate system. Now, here comes what you start calculating, you start asking yourself about the interaction of these modes. And the first thing you notice is the two kinds of interactions. First of all, interactions in general are given by overlap intervals between the different modes. So this kind of object is what happens to couples 2 kk modes of spin 2 kk modes of level n with one of level j. Okay, and this is just the metric in the extra dimension. basically the root G factor you would get. But you have two different kinds of interactions that happen. Remember, the Einstein-Hilbert action is two derivatives. And those derivatives can either be four-dimensional derivatives or they can be the fifth-dimensional derivative. So you have terms involving no derivatives in the extra dimension. You have terms involving the derivative in the extra dimension. So you have different kinds of 3-point and 4-point couplings that appear. The first thing you realize, though, is that at this point, I'm just focusing on the self-interactions of the spin-2 modes. I'll come back to the radion. It's interesting later. What you notice is you can simply use the form of the Sturm-Liouville equation and the boundary conditions to re-express all of the interactions involving derivatives in terms of the interactions that don't involve derivatives. It's just simplifying that number. And again, you're starting to see that this analysis is going to depend on the Sturm-Liouville nature of the mode expansion in the extra dimension. Now, when
This is the size of the extra.
it's the size, and it's because we chose a bad normalization because the B's have different they have different mass dimension than the A's.
So you fix the size.
Yeah. Correct. We're just so again, this is I come back to the stabilized model later if I have time, but we're just doing the simplest RS model to start with. We're doing fluctuations around the naive RS metric. Now, you plug that in, and you ask yourself, what is the analytic form of this M5? Remember, we take our full scattering amplitude as a function of center mass energy and scattering angle. And again, for simplicity, we're doing elastic NN to NN. And you ask, what does its expansion look like in terms of powers of center mass energy squared, starting with center mass energy squared to the 5th power or energy to the 10th. And you get a compact expression times this combination of couplings. Now, if you look at this combination of couplings, you'll see something interesting. It has a square of this coupling and has this coupling. You take the square of this coupling sum over J and you compare it to this. The square of this coupling involves two products of psi J summed over J. You can use completeness. And completeness, which is a general property of the solutions of your Sturm-Liouville problem, will tell you that this vanishes. Okay, so this is the analytic expression for why it really does vanish. And you can also see now, it didn't actually depend on the particular warp factor. It depended on the general Sturm-Liouville nature. Well, more than that, it had to be a Sturm-Liouville problem of this form because we had to count where these warp factors, but if it was an e to the minus 2 AY for any reasonable AY, and e to the minus 4 AY, I would have gotten the same answer. Yep, K0 works too. That flat space works too. Flat space is even easier because the infinite sum actually turns into just a couple terms. But
that's what I was thinking. So in some sense, in the flat space, everything is much simpler, right? You don't have it. And then you give an amplitude, you just need to a couple of times.
I should say I'm at 1:30, so I will keep going as long as you want me to go. But I can stop.
But it's fair to say that I can always choose this basis, but then my masters will not be very.
You mean I could have chosen to expand?
Of course, of conservation of the number, but then I will have a mass mixing of some sort. But then if I take that into account, that mass mixing, it's clearly that it's not going to generate any energy problems. It's like with the neutrino mass. Well, when
I agree that would tell you that the leading term vanishes, right? But we've got 3 subleading terms also. And I'm not sure that that's sufficient to tell you that. The subleading term, this turns out to be the coefficient. Okay, not surprisingly, it's 2 powers of energy less, which is why it has mass chords in it. But you can use the Sturm-Liouville equation in completeness to show that this one vanishes. Okay, so maybe there's a way of re-expressing it in terms of the flat space wave functions. I hadn't thought about it, but then you keep going. Well, so this just says the first 2 things are true. By the way, those 2 sum rules are exactly the same, down to the factors of 3 and the couplings involved. Those are exactly the same couplings that Chaba and John and company realized were at the bottom of the cancellations in the Yang-Mills theory, and that allowed them to generalize to make Higgs-less models. And as I was talking with Jen earlier, I wonder if this is some remnant of the double copy of gravity being a double copy of gauge theory at some level. I certainly don't know how to make that explicit, but it's intriguing to me that it's precisely the same combinations of couplings that enter in the first two. No, well, this is the amplitude. Sorry. No, it doesn't. No, it's not obviously a square. No, no. Okay, what about now? If you go to order s cubed and s squared, at order s cubed and s squared, the scalar exchange starts to contribute. In the first two contributions, they only came from the exchange of spin 2 KK modes. At s cubed and s squared, you have additional contributions that come from the radion, and this is the coefficient of the s cubed term.
But eventually S cube term is vanishes as well, or what is the result?
Say that again. I'm sorry.
No, what is the final amplitude? It is S cube also vanishes or not?
It does. S cube does vanish, and I will eventually be able to prove it, but we couldn't prove it for a few years.
Yeah, but then you finish up with what power of S?
S.
S,
S
I see.
vanishes, and S squared also vanishes.
I see. Yeah, but S is still looks non-realizable, or it right as well.
S is
It's
still
like
non-realizable, just like gravity is not absolutely.
yeah, like gravity. I see. Okay.
Yeah,
Okay.
But the behavior is no worse than you would have gotten in flat space gravity.
Yeah, I got it.
So for this to vanish, you have to have a relation between the radion coupling and all sorts of couplings and the spin 2 spectrum and coupling. This is what this is just as it comes out. And as I say, for the first several years, we had no way of proving this relation, because now it doesn't involve just the spin 2 wave functions. It also involves the spin 0 wave function and overlaps with the spin variable. So you need some kind of way of connecting the spin 0 sector with the spin 2 sector. And at least naively, and in fact, in unitary gauge, it's hard to see how there is any one. And I'll show you how it comes about. But to cut to the bottom line, here's the coefficient of S squared. It turns out the way that the radion coupling appears at S cube, if you assume this is true, if you assume this is true and plug it into here, you get a relation you can prove from the spin 2 sector alone. Again, I don't know why that is the case, but so we had to summarize, we had 4 relations that had to be shown between relating masses and couplings for S to the 5, S to the 4, S to the 3, and S to the 2 cancel. We can prove 3 combinations of them. There's one combination we're not naively able to prove, at least initially. There's one interesting phenomenological implication of this immediately, and this we didn't realize. When we posted our paper, Bonifacio and Hinterbeckler posted a paper saying, we have exactly the same sum rules. They were looking at it from a different point of view. They were doing the same computation. They were not looking at RS. They were looking at a general possibility of Ricci flat compactified extra-dimensional. RS is not Ricci flat. That R is the cosmological constant. That's what gives you the warping. But in some sense, Ricci flat is the generalization of flat, right? But they were able to show the same set of sum rules algebraically.
Related to your Stern-Liouville comment, right?
Exactly. Now they noticed something interesting though. They noticed that if you assume the S cubed and S squared sum rules, remember that we were able to prove that didn't involve the radion, and the S to the 4 sum rule, you could rearrange these in this way. So for any consistent set of amplitudes where the S squared, S cubed, S to the 4th, S to the 5 vanish, this relationship is true as well. And they said, oh, this is interesting, right? You have a KK tower, you have the lowest massive state, and you'd like to know, is there a bound on the second massive state? Because would you, for example, be able to take the second massive state and make it really, really heavy? That would be phenomenologically interesting because it would look like, sure, it wouldn't be massive gravity because you have a massless graviton also, but you have a massless graviton, one massive spin 2 mode, and then some large gap in your spectrum. That would be interesting if that were possible. It's not possible. It's not possible because if you apply this to the lowest mode, you can see that all the terms in this expression are positive except this one. And therefore, there's a bound. The second massive state cannot be any more massive than what happens in flat space, twice the mass of the first one. I think that's kind of cute. I have no idea, it did not occur to us. But the same algebra applies in ours.
But maybe, I'm sorry again to interrupt, but still, it looks like, so your result correspond to, no, I mean, in terms of what we discussed before, that the massless limit does exist in this case, right? So,
No,
so you do.
I think it says the opposite, right? Because the massless case would be M2, it would be going into a region where M1 over M2 goes to 0, and you can't go to that region.
No, not about M2, but just that in terms of the behavior in S, there is no it's not like no division on the mass, so there is only Planck mass there.
You can take a tower and make it heavy. Yes.
Yeah, right. And in this sense, it's like a kind of similar to Higgs mechanism, because Higgs mechanism provides this, say, for the vector theory, and you are providing this for this theory as well, that massless limit does exist. I mean, and it is your kind of, and you are saying that it's kind of generic statement actually, when you're going from extra dimension.
I'm not quite sure. I don't think so. I think this, what I would have been interested in is the idea that you could have one massive spin 2 mode and everything else being very heavy. And
no. I'm trying to limit myself by this limit when mass goes to 0. And in your case, I agree that, no, I mean, about what you said about second excitation or whatever, but whatever it is, say, for example, for next spin 2 particle, I think the massless limit also would exist, be existing.
You're absolutely right. You can view this as, in retrospect, you can say this was all obvious because I could take M1 to 0 and reproduce the 5-dimensional.
Right.
Is that what you're saying? Yeah, I agree.
Yeah.
I would not that smart. I agree. Okay. All right. Same thing with dark matter scattering. Let me, we're already running late, but let me just tell you what we've been able to show, that how this is all related to the underlying diffeomorphism symmetry of the 5-dimensional theory, and how you can understand this from the point of view of the equivalence theorem. Again, I want to remind you of the analogy between in Yang-Mills theory, right? For spontaneously broken Yang-Mills theory and unitary gauge, it may be hard to understand the properties of the scattering amplitude. But when you go to a Toth-Feynman gauge, the power counting is obvious, and then gauge invariance tells you that the two things have to be the same. So same thing, we use conformal coordinates in this case, and the expansion of the metric is much easier to deal with. We're now going to a Toth-Feynman gauge. So in a Toth-Feynman gauge, you have more degrees of freedom. You have unphysical degrees of freedom that would have been set to 0 in unitary gauge. So in this gauge, you have an entire tower of scalar modes, not just the 0 mode, and you have an entire tower of vector modes. And the gauge fixing, the unitary gauge fixing, would set it enables you to set this tower to 0 and everything but the lowest one in the scalar to 0 to go to unitary gauge. But in Feynman gauge, you're in general going to have those states as well. Okay. Now in conformal coordinates, so here this depends more on the RS structure. In conformal coordinates, this is the way that the warp factor looks, the way that it appears. And this is essentially Einstein's equation for in the bulk for this warp factor. Now, if you think about it, one of the crucial things that happens in a Toth-Feynman gauge in a gauge theory is there are no spurious poles, right? There's no poles except either where there are physical masses of states, like at MW and MZ. In a random C gauge, there would seem to be poles somewhere else, and you have to work really hard to show that those poles never appear in any scattering amplitudes. But at C equals 1, what's crucial is that the Goldstone boson masses are degenerate with the gauge boson masses, and all the poles happen just where the gauge bosons have a mass. This is kind of odd from the point of view of extra dimensions, because this is a theory with spin 2 modes, spin 1 modes, and spin 0 modes. And naively, if you just think about the wave equations for spin 2 objects, spin 1 objects, and spin 0 objects, they're different, right? You know, the way this shows up is the scalar modes are proportional to J0, and the vector modes are proportional to J1, and the tensor modes are proportional to J2. And the eigenvalue equations tend to be, you know, equations for zeros of combinations of those functions. So naively, it's hard to understand why the tensor vector and scalar modes, at least for me, it was hard to understand how it's going to turn out that scalar vector and tensor modes have the same masses, which they have to have if there is a consistent Feynman gauge in this theory. And it turns out that they do. And the reason that they do is that the mode expansions for the spin 2 and the spin 1 system are related. They turn out to be two eigenvalue systems related by an n equals 2 supersymmetry. And the spin 1 and spin 0 modes are related, and they also have a separate spin 2 quantum mechanical supersymmetry. I'll explain what I mean by that in a moment. And therefore, all of the states end up being degenerate. And in fact, you don't have massless states where you shouldn't have them. So let me just remind you. So this is an eigenvalue equation. You know, an operator acting on F is lambda F, right? Just a regular eigenvalue equation. If the operator has the form d dagger d, now there's a lot going on in that, right? So I have in mind, this is some first order differential operator d. This is some adjoint to that first order operator. So in order to define the adjoint, I have to have told you what the boundary conditions were on my wave functions, because I have to be able to integrate by parts and define what I mean by an adjoint. So implicitly in here, having found a way of writing my operators d dagger d, I've actually also restricted myself to a certain set of boundary conditions associated with my object. Now, if my operator is d dagger d, you can ask yourself, what happens to the operator d dagger, right? It's not the Hermitian adjoint, right? D dagger d, the Hermitian adjoint of d dagger d is d dagger d, right? So instead of d dagger d, I want to look at d dagger. Okay. What you can show is that if the operator is of this form, this system has exactly the same non-zero eigenvalues. You don't know about the zero mode, but all the non-zero eigenvalues are the same. Why? Because if I look at this quantity, d dagger d of f of x, I can reassociate. I can write that as d dagger df, which is lambda df. That means df, if I choose an f with eigenvalue lambda, then df is an eigenvalue, eigenvector of d dagger with the same eigenvalue, unless df vanishes. So everything but the zero mode, the spectrum is entirely the same except for the zero mode. Okay. Now, I purposely wrote this in small print so it can't be seen from the back of the room. So I'll try to walk you through what it is. This is so you expand your tensor mode in Fs, you expand your vector mode in wave functions G, you expand your scalar modes in wave functions pi. Here are, it turns out, the system of eigenvalue equations associated with the tensor and the vector. And they have exactly the form d dagger d and d dagger, where this is what it turns out to be. And here you have the warp factor A coming in. And now again, I've generalized back to what happens for a general warp factor, as long as this is true, okay? So the vector, so that tells you every mode except the zero mode have the same mass for vector and for tensor. And that's exactly what you want, because the vector actually has no zero mode. There's no massless vector in this theory. And all the massive vectors correspond to the vector Goldstone bosons that are going to be eaten in unitary gauge by your massive spin 2 particle. And they have the same mass in a Feynman gauge, which you thought you should have in order for gauge invariance to work. But that's not enough. You also have a scalar. And so you need to now relate the scalar mass somehow. And it's remarkable. And this comes from a paper by Lim and collaborators. I was only aware of when we looked for it in 2007. They noticed in RS that the mode expansion for the vectors and the scalars, that basically, first of all, the mode expansion for the vector, the mode equation for the vector can be written as d dagger or as d bar dagger d bar for a different d. And this are equal only if Einstein's equations. So it relates the consistency of the classical solution of the background. If the classical background is consistent, satisfies Einstein's equation, then the vector equation can be written in two ways. And the scalar equation is coupled to the vector equation by a different supersymmetry. Yeah. And you can write it, and the amazing thing is you can write it these two different ways for this one. Yeah.
But the fermions aren't there.
No, so again, this is not space-time supersymmetry. This is just quantum mechanical supersymmetry.
No, but the fact that supersymmetry is more or less immediate after you wrote that Hamiltonian is d dagger dt, right?
Yeah, exactly. Because you would normally say, right, you can the supercharge times the supercharge.
Yeah, sure, yeah.
Exactly. That's the sense in which it's supersymmetry. Absolutely.
Yeah.
So again, this is also good because it means the vector and the scalar have the same mass, but the zero mode is different. But the zero mode for the radion is there. It's different. So it's reversed, right? These two interleaved n equals 2 supersymmetric systems. And this was the piece we were missing. This allows us to connect the wave function of the vectors to the wave functions of this, the wave function of the tensor to the wave function of the scalar. And to make a long story short, there's some algebra in between, but we can now prove the relationship between the radion couplings and masses and everything else. So all of the sum rules we can prove.
Yeah, but you still because you have this another supersymmetry, you one supercharge would be like D, right? But you effectively you are saying that there is another one as well. There is another analog of D.
Yep, there's a D and a D bar. Yes, exactly.
Yeah.
That's and again the reason that there's both a D and a D bar is only true if the background Einstein equations are satisfied. So it's a nicely, I think, consistent picture that pulls everything together. I will speed up, and you again should tell me when that I should just stop. But basically, you can use this to find that there's a residual hidden 5-dimensional diffeomorphism, right? Your original theory, your 5-dimensional Einstein-Hilbert action had 5-dimensional diffeomorphism invariance. That was spontaneously broken by the background because the background picks out a particular, it's like the background field. It is a background field. But this is the form of a general 5-dimensional diffeomorphism. If your diffeomorphism has this particular form, now expanded in terms of these wave functions that I've defined, both the tensor and the vector ones. So this one has Neumann boundary conditions and this one has Dirichlet boundary conditions. This is what's needed in order for these gauge transformations to maintain what's typically called straight gauge conditions. Straight gauge conditions are the ones where A mu is 0 on the side and the branes are fixed when you move it. So this combination of diffeomorphisms implies this kind of transformation of your different KK modes. And now you can immediately see that the A mu transforms as a Goldstone boson here because it's got a non-derivative term acting here. And the pi n for any non-zero mass also acts like a Goldstone boson. So the pi are the scalar Goldstone bosons and the A are the vector Goldstone bosons in this spontaneously broken theory with 5-dimensional diffeomorphism invariance. And remember, right, the massless field had 2 degrees of freedom. A massless vector has 2 extra degrees of freedom. This has 1 more. Those are the 5 degrees of freedom. That's the degree of freedom counting. And you can now do the Goldstone boson equivalence theorem in this theory. And you can see that in terms of that the longitudinal scattering is essentially the scattering of these scalar Goldstone bosons. And you can do power counting and you can show that it only goes like energy squared. So the energy squared is consistent with everything else. Because you asked about Goldberger-Wise stabilization, you do all of the same things work with respect to Goldberger-Wise stabilization. Let me just say a word about what that is. So far, the RS background had no physics in it that would constrain the size of the extra dimension. What you do in the Goldberger-Wise mechanism is you consider a theory with a bulk scalar field, which is, other than gravity, not connected to anything, whose value on one brane and the value on the second brane are different. Now, and for the moment, you can generalize, or you can relax away from this, but for the moment, just assume that the values are fixed on those two branes. Then in the bulk, you have two different contributions to the energy of phi. You have the gradient contribution coming from the kinetic energy terms, and you have the potential or mass squared contributions coming from it. The mass squared contributions want to make the interval as small as possible because you want to make the volume as small as possible. The gradient considerations want to make the interval as large as possible because you want the gradient to be as small as possible. And so there's a competition between the gradient term and the potential term that stabilizes the size of the extra dimension. And then it turns out there's a complicated mixing that now occurs because your gravitational sector in RS, when you deal with fluctuations about this, you have a background scalar field as well as a background metric field, and everything mixes with one another. And once you diagonalize everything appropriately, and I've written down the equations here that show what happens, you can show that the same kind of interleaf supersymmetries occur. And you can go to a Topf-Feynman gauge, you can show all the scattering amplitudes must grow like energy squared. And interestingly, you find out that these two different supersymmetries are valid. These two things, you can write it two different ways, but only if the background equations of motion, both for the scalar and the gravity sector, are satisfied. So again, it's all consistent with one another. And you can write down a set of some rules. Again, at s to the 5 and s to the 4, nothing changes because scalar exchange doesn't contribute. But at s cubed and s squared, it's kind of the most naive thing you could imagine. What was originally one radion contribution becomes a sum over all the scalars in the theory, not just the radion, but the Goldberger-Wise scalars too. Because I should be careful, right? This theory, before you introduce the bulk scalar field, it had a tensor set of spin 2 KK modes and one radion. And now you've added a bulk power of KK scalars, and all of the scalars contribute here. They all get mixed together in an interesting way, which, by the way, makes their Sturm-Liouville problem to solve for their masses the most peculiar Sturm-Liouville problem I've ever seen. There's a lot of interesting work originally by Chaba and others on how the radion behaves in the Goldberger-Wise model, and everyone looked at it in the perturbative limit with no back reaction. We can do this exactly with back reaction, at least as long as we can solve the equation. So if you use there's an ansatz which allows you to solve these equations. And the Sturm-Liouville problem that you get for the extra Goldberger-Wise scalars is perfectly it's really self-adjoint and everything works, but that's not clear if you don't have the full structure. Because I can't resist, I'm going to try your patience just one more piece to show what we've done more recently. And this actually has to do with something that we discussed, Tony, when you were visiting, which is so far we've considered terms that just have a bulk Einstein-Hilbert action. You could imagine putting a brane Einstein-Hilbert action on either end. And I think when you came, you told me, Tony, about some brane bending modes. Indeed, the brane bending modes are important. And basically the point is, again, in all of these setups, you have to be careful to be able to disentangle the scalar fluctuations from the tensor fluctuations. But since those mixing are determined by the trace, they're different in 5 dimensions than they are in 4 dimensions. So the transformation you need to unmix scalar from tensor in the bulk is different than the transformation that you need to unmix scalar from tensor on the brane. And there's no way of reconciling that without adding an additional auxiliary field. Its value is entirely determined by the radion field, but it's an actual degree of it's an extra coupling. And so what happens is in the metric you get extra terms. These extra terms give you couplings to the scalars. This delta ultimately is just in a Topf-Feynman gauge is essentially another factor of the radion, and this gives you extra terms that change. And this is what I wanted to say. It turns out to the 5 and S to the 4 vanish, but S cubed doesn't in this theory. And so you can do things like you can say, well, here's the RS scale in this theory. Here's how the second KK mass behaves. And by the way, if you have a large enough brane kinetic energy term, you can make M2 larger than 2M1, but not much. You can't take it to infinity or anything crazy. But now I think this is what Akali was saying too. Once you have a behavior that goes like S cubed, that means that your dynamical scale of your theory, you can't take the M goes to 0 limit anymore. The dynamical scale of your theory depends inversely on the mass. And so there's an additional cutoff which becomes, relevant as you start to increase this node. I'm sorry, I know I've tried on your patience, but I promise I'm done. I'm happy to answer questions and discuss anything further. But thank you very much for your patience.
Yeah, Sekhar, it's my fault, so I'm sorry that you took more time.
What's that?
It's my fault,
no.
I
I'm
misspoke.
glad you came, but I knew that if you came, that it would take longer.
Okay, does anybody have any more questions? Okay, a lot of questions. Well, if not, of course, Sekhar would welcome people stopping by with their questions. Down in the office on the same as usual. Well, let's thank